everything else out of the way, you ready to get started? You just want to jump right in?
Yeah, let's do it. I have the link
Yeah,
on
I'm in here.
Discord.
Yeah, I see you're in here. Cool, cool.
Okay.
So I'm just gonna start the timer real quick, and let's get to it. So for this question, I'm gonna give you an input, and this input is going to be a vector of strings, an array of strings, however you want to think about this. So it looks like that, and it's going to contain a couple of words. So words can be things like ABC, BCD, XYZ, like A, B, 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 like just some quick examples. And I want you to return a grouping of these strings. And the way I want you to group these strings is I want you to group the strings together that can be shifted to create the other strings. So for example, if I look at A, B, and C, and B, C, and D, what I see is that if I shift all letters from B, C, and D to the left by one, B, C, D also becomes A, B, C. So these two strings would form a valid grouping. Similarly, X, Y, Z, if all things are shifted by 24 letters, this also becomes A, B, C. So in this example output, I would expect you to return to me something like this. So we can see here that A, B, C, B, C, D, X, Y, Z are grouped together, and then A, B, 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 B is by itself because it cannot be transformed into the other strings. Does that make sense?
Yeah. Okay. Yeah. So I can already kind of get a good idea of what I want to do here. Like let's have another example input. We'll say I don't know. We'll say A B C D E F G H G H H H H. Would that also be grouped with A B B B B?
Yes, that is correct.
Okay, yeah, so I think what I want to do here is I examine these strings and I look at the difference, like position. So here let's say A is position 0 or something, and B is 1 because B is an offset of A by 1. And then C relative to A would be plus 2. Um, and then I could have that like template or rule apply to these. So yeah, I could maybe have like a dictionary, um, where the key is, a tuple of that, 0, 1, 2. And that would be these three because I look at the letters and I see that, this is plus 1, plus 2, plus 1, plus 2, on and on. And then the other key would be 0, 1, 1, 1, 1. Um, and then yeah, that would take in these two inputs. So yeah, I think so yeah, I would just be looping through this. It would probably be yeah, it would be big O of n time. I just need one loop. So I would be like making this template, putting that in dictionary. I convert this string into the template. If that string is in, or if that template is in our dictionary as a key, then we just append it to what we have so far. And at the end, I'm just going to return all of the values. Does that sound good?
Yeah, sure. Are you sure you've gathered all the information that you want from this?
Um, all the information. Okay, yeah. So what happens if we have like some sort of looping, I guess? So instead of XYZ, YZA, how does that work?
Yeah, that's a great question. So, for the sake of this problem, let's say we're using, for now, let's just limit it to lowercase alphabet letters. So, it'll look like A, B, C, D up to X, Y, Z. And what's
Uh,
going to happen is, for this problem, we can count to the right of Z as A and to the left of A as Z. So,
Okay, so it like loops around, I guess. It
exactly.
wraps around.
Yep.
Okay.
So for the sake of this question, to give you some clarity, YZA would actually be grouped with ABC and BCD.
Okay, yeah. Yeah, in that case, I convert these characters. I could convert these character into their ASCII values and then do a mod, um, 26. So I would have to, yeah, if I convert these characters to their ASCII values and then subtract it by the offset, I'm not too sure what A starts with, to be honest. Well, actually, I don't need. I can just do 8 minus A, and then that would give me 0. Okay. I do the ASCII minus ASCII of A, and then yeah, yeah. Okay, cool. So I think that's all the information I need. Basically, it's just convert character to ASCII, subtract by ASCII A. Um, yeah. Okay. Should we get started then?
Yeah, let's go for it.
Okay. So I'll be defining um group by offset. It would take in a list of strings. We'll just call these strings. Okay. So yeah, let's first create our group dictionary. Group dict equals that. Should we just go ahead and get started with the helper function, or I'll just lay out the work for the looping. So for string in strings, um, we're going to maybe create we'll create a offset tuple equals get offset tuple. That would take in our string. And then once we get that offset tuple, we're going to see if offset tuple is in our group dict, then we're just gonna go ahead and do group dict dot append the string that we were examining. Um, Otherwise, we're going to have to add group dict dot or group dict offset tuple is going to be equal to string as our initial list. Okay, and then at the very end, we're just going to do return group dict dot values. So yeah, that should
Okay. Real
that
quick,
loop
I'm
should
not sure if this is just my unfamiliarity with Python, but is this meant to be strings over here? Line 20?
uh yeah, that should be strings. Yeah.
And the other thing, line 23, what are you appending your string to here?
Oh, very offset tuple here. All right, yeah, my bad.
Oh, no worries.
Okay. All right, so yeah, let's also create like a helper function up here. Define get offset tuple. It takes in the string for character in string. We're gonna do. We're gonna first create that tuple, I guess. First, we'll make it a list, and then we'll convert it into tuple at the end. Otherwise, we can't really like mutate it. So yeah, let's say offset list equals this. So for character in string, yeah, so we'll have to get our first character. Actually, another question. Is it possible to get an empty string?
Yeah, let's handle that case.
Okay, yeah,
So
then
the way we would kind of expect this to work is, let's say that empty strings will be grouped with other empty strings.
okay. So if not string, then we're just gonna return an empty tuple. Um Yeah, so that would handle the empty string cases. The rest of this will still go as expected because it's an empty tuple. Okay. So for character in string, we're going to need to first we would have to normalize our first value. So for example, A needs to be 0, but like if the first thing we saw was BCD instead, we're gonna need to know that we're gonna have B as 0, and we do that by doing B minus B. So yeah, let's do that first. First value or first SC equals, or actually, yeah, we'll do first value equals ord, um, ord string 0. So then for the character in string, starting from index 1 to the end, we're going to be doing, okay, so the first value needs to be put in the two. No, it doesn't need to, not yet. Actually, yeah, we're going to loop through the whole string. We're going to do first, we're going to do ord character minus first value. And that is going to be appended to our offset list. That append that. So if this is B, then we're going to subtract by B, and that is going to give us 0. But we also need to handle the wraparound, so we're going to do this mod, how many letters? 26. So yeah, there's 26 letters in the alphabet, and once we reach like the opposite end, which would be A probably, so A minus B, that'd be like negative 25, or yeah, that should return.
So two things real quick. I have a guess as to what this does, but please educate me. Ord, like what does ord return?
The ord will return the ASCII values.
Okay, sure. And let's say that yeah, you have a minus b. So this would be, or let me think. Let's say you have like a minus z. So this would give you like negative 25, right? So in Python, if you take a negative number and you mod it, does it force a positive value?
That's a good question. That would well, what do we want exactly? Like, is even if wait, so I might be unfamiliar with how mod works exactly. So like, if this were like -1, um,
Yeah, so I'm asking you, would that return negative 1 or 25?
I've never actually like
All right, that's
tested
okay.
that.
That's okay.
I'm
We can
good.
actually write some logic to handle it to force the same value, right?
Yeah, if it is -1, um, well, do I even really need to do the mod then? Like, do I just do okay? Um, do I just do 26 minus the ord? Like, would that give us what we want here? The lowest being the highest number possible being 26. Um,
So,
yeah, I
say for
mean that.
example, like negative 2 and 24 are the same thing, right? As far as this mod goes. Uh, I'm not sure how this will interfere with your thing, but I think it might be convenient to have everything be a positive number. So, what's one thing you can do to make that happen?
I mean, if I take the absolute value, would that?
Well, so negative 1 would map to 25, right?
Yeah.
And -1 absolute value would be 1.
Yeah, so like that's not what we want, but then how can I make them all positive? Like maybe I add 26 to everything and then that'd be kind of weird, but I mean, I
Well, I think it does
guess
the job, right? I think adding 26 to everything might not be what you want, though, because let's say the value is already like 5. You add 26, then it becomes 31.
yeah, but then the tuple will return 31. And then like, if we have, our like it's all relative to the first value anyway. If something matches, it's going to also return 31. Um, yeah, if that makes sense.
So the problem is 31 and 5 would map to the same character pairing.
What if?
So 31 and 5 would map to the same character pairing, right? Because 31 and 5 at the end of the day are both shifts of 5 characters. So it would be A to F in both cases. Let's do something. What if we just did this modded by 26? The other way
Uh,
this might have worked is you could have done the mod of 26, and if it was somehow still negative, you just add 26 to the number. All of this, of course, assuming that I don't quite understand how the mod in Python works, but this is something you should probably go learn. But you should know
yeah,
if it'll always force a positive value or if it can be negative as well.
yeah, sure. I okay, yeah. I always thought mod never returns negatives, so but all right. So we get our offset list. We loop through all the characters in the string. That is weird. Why is this? Oh, okay, never mind. Okay, so we're going to return the tuple, or actually, let's return offset list. Um, Actually, yeah, we're gonna have to return this as a tuple. I actually kind of forgot how to do that.
Well, feel free to look it up right now.
Yeah, sure. Oh wait, right. No, never mind. I remember. It's just literally this. Okay, so yeah, we return the tuple and then I think everything else should work. Yeah, let's
Yeah, sure. Do you want me to walk me through? Yeah, there's just this case up here.
uh which edge case, the YZA?
Yeah, let's just do kind of like these 5 words put together. Kind of see what happens.
Okay. Um so yeah, I'll just do that down here. So our input BCD. Okay, so first we created our group dictionary. Group dict. It is empty. Now, for string and strings, we're currently going to be looking at letter BCD or strings BCD, right? Um, and so we're gonna jump into this function, the tuple. We're gonna initiate an empty list. So offset list equals empty. Now, since this is not an empty string, we're gonna skip this line. Now, the first value ordinance string 0, that's going to be B, right? So first val equals um it's gonna be equal to 2 because B, or actually no, not 2. It's gonna be like 97 or whatever B
I
is.
get what you're trying to say. You can just say the
Yeah,
second letter
but let's
wrong
just say
again.
2
Yeah.
for simplicity. Or is it 1? Yeah, let's just say 1. A being 0. Um, and then we're gonna, loop through. So we're gonna go B. B minus B is equal to 0. So our list is 0 for now. Then we're gonna do, what is it? C minus B, that's gonna be 1. D minus B, that's gonna be 2. And so that is the tuple we are returning to our group dictionary. So 0, 1, 2, with the values of our string, which is BCD. Um, yeah, so that, oh wait, no, we skip here. Okay, so yeah, that is what our values would be inside a list. Now, we're going to look at the next one, ABC. Pretty much the same thing. So the first value is actually going to be 0 this time. Everything's going to be subtracted by 0. B minus 0. C minus 0. That's going to be 0, 1, 2.
Yeah, let's
So
talk about YZA real quick. We can go ahead and skip to that.
yeah, sure. So let's do YZA. Y being 25 or 24. Z being 25. So Y is 24. That is our first value. 24 minus 24, that's going to be 0. 25 minus 24, that's going to be 1. And then 0 minus 24 plus 26, that is going to be 0 minus 24, negative 24 plus 26. Did I do this offset wrong then? Or is Y actually 25?
Well,
25.
0 minus 24 plus 26 sounds like 2, doesn't it?
Yeah, which is not what we want. We wanted a final value of, oh, actually, yeah, you're right. 2. Okay, so yeah, that would work. We got there 2. So yeah, therefore Y, C, A is in this grouping.
All right.
Um, yeah,
Uh,
so
sure. Real quick, just you don't have to type this out. Just kind of tell me what A B B B B would be.
A, B, 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 B. So, starts at 0, 0, 1, 2, 1, 1.
Right, and that would go into its own bucket. Okay, cool, cool, nice.
Yeah.
So would you mind walking me through what the runtime complexity of this would be?
Yeah, so given n strings, we're just doing like one loop. We're appending to the dictionary. So yeah, because of that, this is going to be big O of 1, or I mean n.
Okay, so let's talk about that a little bit. In in this loop, you're calling this loop n times. Well, you're performing n run throughs of this loop. Is everything in here constant runtime?
Um, I mean, if I'm checking for offs, like if I'm checking if this exists in the dictionary,
Yeah, yeah. Let's talk about getting the actual tuple.
I mean, it should be constant time lookup. Um,
I'm not talking about your lookup. I'm talking about getting the actual tuple in line 34. What
yeah.
is the working logic of this?
Yeah, this is we're examining each letters. Yeah, if we want to assign another like runtime, it would be like say each letter there are like n amount of letters, I guess. Then the runtime would be n times n because we're doing one loop through all the letters.
Okay,
Um,
yeah, that
yeah.
sounds good to me. What about the memory?
The memory is also going to be linear time since um, we're basically making a structure to store everything that we've seen. Like this dictionary is going to contain all of the strings, and this list is going to contain all of the characters.
Okay, good. One last follow up question for this. So, at the beginning of this question, I told you that you could assume that we're dealing with just lowercase English letters. Let's say we wanted to use a different language. maybe with different characters. Actually, for this problem, let's stay limited to the ASCII library. But let's say hypothetically, I have an alien language that combines, say, uppercase English letters, lowercase English letters, and then like a couple of digits, maybe just 1 through 9, and then a couple of special symbols as well. Exclamation mark, pound, dollar sign, percent. You don't have to necessarily implement this, but talk me through kind of what things would change if we wanted to create some kind of support for that.
Yeah, so I'm not too sure what you mean though. Like, are all of those symbols still going to be unique to each other, or are they gonna have like overlapping values, I guess?
Yeah, so I'll give you a little bit more detail. So I'll type this up in line 16. So in this question, if you look at line 5, you can see that I've given you the alphabet essentially of lowercase English letters. What
Yeah.
if instead this alphabet looked something like, A, B, C, D, E, F, and then dot, dot, dot on X, Y, Z. And then you had the lowercase letters up to X, Y, Z. And then you had, I don't know, a couple of digits. And then you had like some special symbols. What if this was your alphabet instead?
So yeah, then we would have to change the values of like our mods and like how much we're adding um by because if they're all like unique from each other, then all of these logics are basically the same. We would just need to change this constant from 26 to however many characters we actually have
Okay,
in our language.
is there anything else you think you might have to change up?
Anything else? Not that I can immediately see.
Take a couple of maybe 20, 30 seconds, think about it.
But so like the lowercase a and the uppercase a are different from each other, right?
Yeah, they're different from each other.
Okay. Um, yeah, so I mean if I change to 26, that should handle like our wrappings. So what else would I be missing exactly?
Maybe this will help you set you straight. So everything I've given to you so far has been really nice and ordered. What if, just because I felt like it, for the first uppercase alphabet, I reverse the order, so it looks something like this.
Oh, okay, interesting. Then in that case, instead of turning these into ASCII symbols, then I would have to do some sort of mapping um to like get the order into like the literal values, if that makes sense. Um, but like
Yeah.
we're using
So
ASCII here because
let's
that's
say
conveniently done for us.
in your function call, line 32, let's say I also pass you like a custom alphabet. What sort of processing would you do with this alphabet to support this new intended behavior?
Um, well, I mean, if the alphabet is given to me as a dictionary with the key being the character and the
Let's
value,
say I'll give it to you as like a string or something.
okay, then I will convert it into a dictionary where the value is or the key is the letter and the value is the value. And then instead of here, the ord, I would just be doing alpha dict character. Yeah, that would return the value.
Okay, cool, cool. I like it. And I'm assuming for something like 26, would you still hard code a value, or what would you do?
Uh, 26 or 25. Oh, here.
Yeah, so what would you do with these values?
It would just be the length of output. Or actually, I shouldn't type that in here. length of alpha.
Okay, perfect.
Uh,
Nice. That's all I had for this question. If you have nothing else, we can move on to the next one.
okay, so yeah, let's assume that was round number one. In terms of timing, did that like make the cutoff? Um,
Yeah, so we are basically exactly 30 minutes in. I think you started writing code around the before the 10-minute mark. You dissected the problem reasonably quickly. The shifting here was explained very quickly and pretty well. Um, my advice to you for when we were running through this example between line 44 and 50, it was explained to me very, very slowly. Um,
yeah.
I'm not sure if this is a comfort thing, but in the future, I think it could benefit you if you are able to talk about your thoughts a little bit faster, because I think being able to communicate your thoughts really quickly but still clearly, maybe you could have pushed this like 5 minutes faster or so. But everything else outside of just the overall time, I like the way that you explained get offset tuple. I liked how you wrote the entire like main idea first. I like how you wrote a declared a helper, told me what the intended behavior was, and then came back to that later to kind of present as much of the problem as you could in as short of a time as possible. Yeah, just a little bit faster, but otherwise, I think this is pretty solid performance. First question.
Well, thanks. Would it be worth it to just skip ABC in the example and go to our edge case then?
Yeah, so I might do something like this where I can say, okay, well, we see that A would normalize to, uh, if A is 0, then the first letter is A. We see that we don't have to shift anything at all. So B and C would just be 1 and 2. So the tuple is 0, 1, 2.
Okay, yeah.
Yeah.
All right,
You
cool.
don't actually have to work through each example specifically, especially if it's very obvious what is happening.
Yeah. Okay, yeah.
That's just like a use your own judgment thing. But yeah, this is good. Do you want to leave this in here so you can submit it later?
I'm gonna copy and paste to the Google Doc, and then we can go ahead and clear that out.
Okay,
Okay.
sure. Let me know whenever you're good, and I will reset
Yep.
the timer. Ready?
Okay. Yeah.
All right. So for this next question, I'm going to pass into you a grid, a 2D grid of characters. So let's say an example grid might look like A, B, C, D, E, F, G, H, I. So I've given you a 3x3 grid of just characters. And I'm also going to give you a word. So let's say ADEF, just hypothetically. What I want you to output is if we can create this word by traversing our grid. So in this case, we can see that it's true because if we start at the top left, go down 1, go right 2, we've created ADEF. So in this case, it'll be true since ADEF is found in the board. Okay, so rules for your traversal. You can only use each tile once, and you can travel 4 directionally.
Okay. Um,
I'll walk you through another example output. So given this same grid, let's say the word it was instead BEHE. So this would be false because even though we can traverse B down, down, up, this would be reusing the letter E. So it's no good.
yeah. And we can't like we can't you can't go from like B to H, right? Like none
Yeah,
of that.
yeah.
Okay. All right, I think that's all I need to know then. This seems like fairly straightforward breadth first search kind of traversal where at every letter I could just call um, um, can match function or something like that, and then I would start looking around the four directions, and as long as we as long as the current letter is matching our current. Oh, okay. So for the input, is it just one string or is it like a list of strings?
So for now, let's just say it's a singular string, and then you're given also the 2D grid. Let's say it's like a vector of vectors, something like that.
Yeah, I mean, yeah, in that case, I think like just doing a breadth first search traversal is probably the best way to get through this. Yeah, I mean, I think that's really it. I iterate through this list. If the first letter matches the current like letter we're looking at, then we can start traveling from there in the direction, and we'll also have a list or a set that would keep the visited coordinates in there as well, so that we don't like step into the visited coordinate. Um, and then yeah, by the end of that, if we have not been able to find a match, we'll just return false. Otherwise, we'll return true if we found a match. Does that sound good?
Okay, I agree with most of that. I think that's a pretty good start. I'm interested to see how you'll perform breadth first search to solve this problem. I think you might run into a couple of issues with this, so let's talk about this a little bit. Um, you mentioned earlier that you want to keep a set of tiles that you visited already.
Yeah.
Is this something that you can easily do with breadth first search?
Um, I mean, yeah, I at every state, I'll have that set of tiles um maintained in the stack, or I mean in the queue. So each element in the queue will be a tuple or a pair, I guess. The first pair um being the letters we've seen so far, and then the second element of the pair or the tuple being the set of tiles we stepped on.
Yeah, so talk to me about this. Let's say we're performing the BFS and we found that our current path is not promising. How do we
Um,
go back from this?
then we would no longer add any more. We would no longer be appending our current path. That would get pruned or popped off.
Okay, so how would you then modify your set of visited cells?
The set of visited cells will here. So like let's q equals this. Um, we'll just say set visited set equals nothing so far, right?
Yeah, sure.
Okay, so then let's just imagine that in our queue, like we're somewhere in the middle. We've seen A D so far, and what our set would look like at this point is imagine if we saw A at 0, 1, and then D at 1, 1, I guess. Um, that would be equal to the current string and the visited um visited current visited. And then so like when we think that the next direction we're looking at, if next tile is promising or matches next letter, then we're going to add current string plus uh next letter, as well as set uh, her visited plus set whatever that coordinate is, row column.
Okay, so is there a reason you've specifically chosen breadth first search over, say, depth first search for this question?
In the end, I don't think it really would it matter much. I guess for like I want to think that in either case, we're assuming that the grid is n by m, and then our string length is z or whatever. Where we're going to be performing breadth first search or depth first search until we've exhausted all options. But I think like at least with breadth first search, we're able to quickly discontinue paths that we don't find promising. Um,
Okay, so talk to me about how a breadth first search expands. How does it actually search the grid? Let's say we
so
started at the E in the middle. We can ignore the word. Let's say we start at the E in the middle. How would your breadth first search spread?
it would look at F, H, D, and then B, or
Okay.
however I want to see it. Um, and then it would go back to this F and look C or I, go to this H, look I to G, to this D, A, G, A, yeah. Yeah, so I mean, I guess like if the word does exist there, then I will find it as soon as possible. Um, if it does exist.
Okay, so what I'm trying to tell you is that a BFS expands more circularly, while a DFS explores one route as deep as possible. But you talked about pruning earlier. Can pruning be used on this as well?
Pruning.
Let's talk
I
about this
mean,
here. I think in line 17 and 18, you've actually described an approach that isn't actually the best suited for BFS. Well, what does this look like more to you?
can you unhighlight it? um, yeah, okay. So if next tile matches next letter, I mean, yeah, I get, yeah, I am like looking at the next state, before I decide if I want to choose a different one. So yeah, I guess that first search would make more sense here. So yeah.
Okay,
Uh,
so
all right.
what I was trying to tell you is that with the BFS, you have to create this set of visited every single time, don't you?
Oh yeah, that's right.
So let's say you start at the E, you go up, right, down, left. Every single time you create this new set of what you've currently visited. I think you could manage this a lot better if you're using a DFS.
Yeah, then I would no longer have to copy a visited set at every state. I could just do this addition subtraction um every time. Okay.
Yeah, sounds good to
Yeah.
me. But I mean, it sounds like you kind of pin down algorithmically kind of like what you want to do.
All right. Yeah. Let's create our is word present function. It would take in our um I guess we'll just call this the matrix. Um and then it would take in the word. Okay, so yeah. Um so let's just go ahead and draw out the overall code. So for row in length, so yeah, if I'm given an empty matrix, if not matrix, we'll just handle that. Return. Do I want to return true or false here? Just false, right?
Yeah, sure. Let's just say
Okay.
assume the word that I give you. Actually, in this instance, let's say I always pass you in a valid word, so its length is always 1. So yeah, if there's no matrix, you'd say false. Yeah, it's good.
Okay. All right. Yeah. We'll default our output to false because we're going to be returning true if we do find the word. Okay. So now for row and length of the matrix, um, then for column and length of the matrix, of the first row. Oh wait, in range, this would iterate from 0 to the length of those dimensions. And then we're going to do perform. Um, all right, let's see. Is found equals um perform search on each of these tiles. So perform search. This would take in the row, the column, and the matrix. Those are the information we would need to do so. If is found, we're going to return true. Otherwise, we're just going to keep searching
Okay,
the rest of the grid.
sure, makes sense to me.
Okay, so now we're gonna create our form search function. It takes in the row, the column, the matrix. Oh, actually, also need the word. So now we're going to look at the first letter. So if word 0 is equal to matrix row column, then we're going to start searching with our, we're going to start creating our stacks and stuff. So let's just say, or actually maybe a simpler way to do this, if this is not equal, we're just going to return false right off the bat. Otherwise, we're going to start initializing our stack because it kind of looks pretty promising so far. Stack.append. We're going to have the first letter of the word. Word 0 inside. We can just keep this as string. And we're going to have our visited set equals set. Okay. So this visited set is going to also have word in it because that's what we've already looked at so far. Now, while stack, we're going to basically, so we see our 4 directions, or I mean, yeah, so right now we've already done our first comparison. So yeah, let's go ahead and start exploring our uh, our 4 directions. So doing that, we're going to do for row diff, column diff in a list of tuples. So 1, 0. The order doesn't really matter here, but all right, 0, 1, -1, 0, and 0, -1. That would give us the 4 directions we're going to be looking at. New row equals row diff. Oh, actually, hang on. I need to pop off the element first. So current row, current column equals. Wait, Oh, okay. Actually, what I can do here is instead of appending the first word, I could just append what the rest of the string is. So we'll do 1 to the end. But I also still need to append the row, column, and then the rest of that string. So remaining characters or remaining string. It is going to be equal to stack.pop off the end. So new row is going to be new row equals row diff, or actually we'll do current row plus row diff. And then new column equals current column plus column diff. Okay, so then we're going to do if is promising, new row, new column, remaining string, matrix. I want to modulate these to keep the logics as separated as possible. So, I mean, if this is promising, then we're just going to go ahead and do stack dot append new row, new column, remaining string 1 to the end, matrix, and I would also go ahead and do visited set dot add word 0. But all right. So I also definitely need to set my base case and condition where if remaining if not remaining string, then we have found all the characters. So we're just gonna go ahead and return true here.
Sure. Okay. I get what's happening here. Is there a reason you've chosen to? Let's think about it this way. So we're creating a lot of strings here, and this is kind of a small little knit. What are you interested in most? So let's say our example is ADEF, and so far we have found AD. What are we interested in next?
We're interested in finding E,
Okay, and let's say we do find that E. What are we interested in then?
F. So, I mean, I guess instead of remaining string, I could do like an index of the string of the word we're looking at.
Yeah,
So
it's
yeah.
fine. It's fine. We can leave it as remaining string. I just wanted to pick your brain about that.
Okay. Um, yeah, sure. We'll revisit that later. So if not remaining string, let's return true. I also need to think about when do I decide to decrement the set? Okay, should be new row, new column here. So when do I decide to take away from the set? I mean, I see not if I don't see anything here. I don't know. Honestly, I think it'd be easier if I just have the visited set in the stack as well. It helps keep the state. Is it okay if I go ahead and do that?
So before you do that, let's actually talk about what's happening when we. Let's see. What do we have with this visited set? This visited set is declared in line 28, and then it's only
Yeah.
ever interacted with in 42, right? And I'm assuming you'll probably use it elsewhere too.
Yeah, it'll be done in the is promising. Um,
Yeah, so let's talk about this a little bit. So let's say that I'm gonna go back up to scroll up a little bit. I'm gonna change. I'll give you a new grid to kind of just for the sake of clarity. Doesn't really matter what I do here. I'll say like something like this. So we can see that AD will very clearly try to branch out up, down, left, and right, right? So let's say that the order we do this in is just up, right, down, left. So it'll do up, right, down, left. Let's say we talk me through what the state of visited set is as we perform this.
So yeah, if we did up, down, right, left, or I forgot what the order is, but we'll just do clockwise. So if I did up, I see that this isn't working. I'm gonna check right. That's not working.
They all do work. It's A, D, E, F.
Oh, they all work.
Yeah, yeah,
Okay.
they all work. Yeah.
Okay. So they all work. The current state of our set would be, yeah, like I believe that's 1, 0. I'll separate these by space to make it easier. On the right, that should be 2, 1. On the bottom, that should be wait, no, not 2, 1. 1, 2. On the bottom, that's gonna be 2, 1. And on the left, that's going to be 0, 1.
So let's talk about the very last one. You're going to traverse between these two, right? If our order is up, right, down, left.
Yeah.
Let's say we do this, okay, and we see that it is indeed promising. What is the state of the visited set when we do this? What does it think about these three?
It should no longer see them as, because we've seen these. Oh, actually, yeah.
Will it?
Yeah, but we're gonna, as we're looking through this, we're going to not add them to the visiting set. Oh, so we're already kind of doing that here because it's only if it's promising that I am adding.
But in this example, they're all promising.
They're all promising. Okay.
What I'm trying to tell you is you're going to have incorrectly flagged visited tiles.
So if it's not promising, we're going to get rid of it from the visiting set.
Well, hold on. This doesn't quite address the issue here. All of these are promising, right?
Yeah.
So by the time you go to the last one, your visited set, because it's a relatively higher scoped set, it's going to contain all the coordinates up, right, down, and left, even though you're only going down one path.
Yeah, that's true. So then the visited set needs to be interacted with.
The hint I'll give you here is I think that implementing this with a stack might be a huge headache. It's doable, but I think there's a more intuitive way you can think about this. The overall DFS approach, I think, is still promising. Can you think of a way to do that without using a explicit stack data structure?
I mean, I could do recursion, but
so what benefit do you think recursion lets you do?
it would allow me to carry over the state of the stack, but I mean, ultimately, wouldn't that be the same as if I were to just put, the set in here? Even like memory-wise and runtime-wise, I think that's essentially the same thing, right?
Yeah, kind of, except we're creating... Remember the initial problem with this BFS that we talked about here? You're creating a new set for each traversal. A new set is created every time, and we wanted to kind of avoid that or make it easier to manage.
But if we do
So
it with recursion, won't that also
let's talk
be?
about this a little bit. So let's look at line 48. If something is promising, what we're saying is we append it to the stack. So we want to mark it as do this next. And
Yeah.
similarly before, in line 49, we also did something with the visited set. We maintained the visited set. But what we saw was that it's kind of hard to do this because we're traversing in 4 directions, and it's possible the visited set is influenced by a previous direction. Because in this stack, let's say we traverse up and we find, oh, it works. We have a match. It's promising. Do we immediately go and search that more? What do we do instead?
We add that to, or like currently in my code.
Yeah, so what's happening? How would
Yeah,
this
we're
stack
adding
look
that
like?
to like the stack.
And then
Um,
what do you do?
and I just keep looking at the other options, add those to the stack.
Exactly. You keep looking at the other options. What does a
Yeah.
DFS normally do?
Um, yeah, I would just go down that first path of C's first.
Exactly. And I think this would give you a much better way of maintaining your visited set.
Okay. Let's do define DFS. Um, same deal. It takes in a row, column, the remaining word for now. Revisit that later, and then it will take in the visited set. And then so instead of this, or this, or even this, instead of stack.append, it also needs to take in the matrix. It takes in the matrix, and then it takes in the visited set plus set new row, new column. So we did our set addition here. If promising, instead of doing stack.append, we're going to do recursive call DFS. Just making sure the parentheses are balanced out. Yep, looks like it's good. If is promising DFS. And yeah, I mean, I will no longer need to worry about subtracting anything from the set because that would automatically be pruned off. If not remaining string return true. So this here we're gonna do if it's promising. We're gonna have to do return DFS. The row, the column, the word, the matrix, and the visited set.
Okay. Yeah.
And that should, yeah, Python's weird, so I have to do it like this way. I will, the definition has to be declared, or the function has to be defined before it's used. And then yeah, so that would overall be how the DFS operates. So now we're going to need to implement is promising, which takes in, these four stuff. Oh, it also needs to take in the visited set. Because we do not want to explore, or we do not want to say something's promising if it's already been visited. So if new row is less than 0, or new row is greater than matrix length of matrix -1, or new column is less than 0, or new column is greater than length of matrix row 1, row 0, -1. That would be our boundary check. We're going to return false.
Okay.
Now, if remaining, okay, if matrix new row, new column does not equal remaining string 0, basically we're looking to see if this is still a promising string. We're going to return false. Now, if new row, the tuple new row, new column in visited set, that will also be false because we do not want to revisit the same coordinates. And at the end, we're going to return true. I believe these are the 3 conditions we're looking for.
Okay.
Yeah, out of bound, next string matches, or next character matches, and has not been visited. Okay. So yeah, I think that should be everything. If is found. Yeah.
Yeah. Cool. Quite the lengthy problem. Do you mind walking me through what the runtime complexity of this looked like?
Okay. Yeah, I mean, let's say worst case scenario, we have something that looks like this example grid here, and then the word is, I don't know, ADZ. Then I would, I'm traversing through the whole grid, right? That's going to be n times m at the very least. And I'm going to need to perform a BFS. So yeah, let me just write that down. A comment. If we go n times m. So then at that, I would also have to perform my depth first search. This is constant time. This function is promising, so no worries there. Now I am looking at 4 different directions, potentially every time. But I'm also looking at potentially the whole grid, right? Like, or not. Yeah, potentially the whole grid. Yeah, this is my DFS could potentially look at the whole grid, depending how the grid looks. So yeah, I would definitely say that the runtime is going to be n times m squared.
Okay. So let's talk about that a little bit. Um, let's say that we're at a random tile in our grid. How many ways can we traverse from that point on? Let's say we're in line 11. We're at this A in the middle. How many other tiles? How many other tiles can I traverse to?
It's going to be 4 at the beginning, right?
Yeah. Now let's say this is a. I'll pad this out a little bit. Make this a Let's make this like a bigger grid sort of deal. Let's say we're at like conveniently towards like the middle. And you know, this grid could be 100 by 100. I'm not going to make that, but let's say it was. How many ways could I traverse from a specific tile?
Traverse from a specific tile.
Yeah.
It's always gonna be the full entire grid, right?
Well, yeah, but right now I'm talking about the singular level.
Yeah, it's always gonna be four then.
Sure. Now let's say I go from one tile to another tile. How many tiles can I then traverse to from the new tile?
3.
Yeah? Now let's say I jump to another tile. How many can I traverse to?
Could be 3.
You're right,
Yeah.
it could be 3. What if I did it again?
Yeah, so it's always gonna be could be 3 until we
Could be
start.
3. And
Yeah,
what's the max number of hops I could make?
the whole grid and times them.
Kind of, yeah, but we have something else that we can think about this in. Can you think? Let's
The max
say.
hop. Oh, actually, yeah, the word itself.
Mm-hmm.
So the max hop is 3 times the and then from every tile it's gonna be that. So it's z times n times m.
Are you sure? So what is z?
Z is the length of the word.
Okay.
All right.
So what I just told you was that for each letter, you can jump to 3 other tiles for your next letter. It's like a tree, isn't it?
Yeah, that would be z to the third power.
Are you sure?
Yeah. Am I? Like, I don't know.
My advice to you for these kind of things is to not guess, by the way. Kind of talk me through. You don't have to provide an immediate answer. So imagine a tree that has a root, and then there's 4 possibilities that you could go down on. And then for each of those 4 possibilities, there's 3 possibilities you can go down on.
Oh,
For each of
3 to
those-
the z power, yeah.
Right.
Okay, so 3 to the z um times m by m.
Yeah, sounds good to me. All right. One last follow-up question, then we can call it. At the very beginning, you asked me, am I only given one word? And I told you, for now, let's assume yes. What if we change this question and you don't actually have to implement anything, just kind of talk to me about it? What might you do differently if instead of a singular word, I gave you, say, a dictionary of words, and this dictionary could contain every existing word on the planet? And I told you instead I want you to either return to me the number of words you can find in this grid, or return to me the set or a dictionary of words that you were able to find. How might you approach this problem a little bit differently?
Jeez.
And this is just a discussion. You don't actually have to.
Yeah. How would I do it differently?
Yeah.
If it's a very massive dictionary, then would I want to consider searching through the dictionary instead? Let's think about that. I mean, yeah, like the grid would be the smaller thing compared to the dictionary at a certain point, right?
Well, we don't know that for sure.
Yeah, we don't know that for sure. But okay, so I mean, like, if we were to modify my algorithm, what's gonna happen is on line 60, instead of like searching for a random word here, the quickest way would be to loop through the words in dictionary. So yeah, it's like 4 word
Okay.
in
Yeah, yeah, you don't have to write this out. Yeah, I understand. So let's say that I gave you K words. What would kind of the runtime of this look like? You already
three
have the solution to
times.
one of them, right?
Yeah, I if there were k words, we're multiplying the amount of words by k here, so this would be our new runtime, 3 to the kz
Are you,
times n by n.
are you sure it's 3 to the KZ? It sounds like you're doing this independently for K words, right?
Doing this independently. So it should be k times.
Yeah.
Assuming that, yeah, z is like the amount of characters. Okay.
Yeah, like on, we'll say like the longest word or something like that. Yeah. Let's talk about how we might optimize that a little bit. So, in what you're doing right now, your perform search depends on the status of a singular word. You're using a remaining string to keep track of how far you are in searching, right?
Yeah.
We can see
So
that
instead
this
of the
is
remaining string, I could do remaining words that all starts with the same, like, yeah, yeah, yeah.
well,
Yeah.
kind of, yeah. So what's okay? So in Python, you have dictionaries, and you can quickly use a dictionary to determine if something is correct me if I'm wrong, but you can use a dictionary to determine if you're on the right path. Think about that a little bit.
So use a dictionary to determine if I'm on the right path. Um, how would that look like?
So the hint I'll give you for this is let's suppose we had unlimited memory. I gave you all of the memory to do whatever it is that you wanted to do.
Do I create a substring? I would create a key for every substrings.
Okay, and what
Um,
would you do with this?
and then the value, um, the value would be the words that the substring originated from. Um, and those would be the words I'm still potentially that are still potentially
So I'll give you
working.
an example dictionary, okay? And we'll keep it small so it's easy to think about. Uh, on line 28, real quick, let's say I give you the dictionary of, I don't know, ABC, DEF, and GHI. What might this look like? How would you
Um,
process this?
oops. So yeah, our dictionary would theoretically look like ABC would be ABC. Here, let's just pretend that there's overlaps or something. So let's just say FBC. Um, so yeah, ABC substring of only ABC, right? But BC is a substring of ABC and FBC.
While this is true, do ABC and FBC really overlap with each other if they have different prefixes?
Yeah, they don't. So
I
then what am
mean,
I trying to do with the substrings?
yeah, so let's say instead I give you ABF.
Then yeah, I would ABC and then ABF. So I'm keeping the prefixes of each of these instead. Um, so we'll do A. That would also be ABC, ABF, and then like whatever that other thing is, GHI.
Do
I
you
don't think we really care about
do
that
you
right
really need to
now.
keep track of these, or can you just keep track of the prefixes? Do you really care that A eventually might become ABC or ABF, or do you just care that A exists?
I see that A exists, right? Um, then I would link that to every other word that starts with the ABCs. Oh, I see. I see what you're saying. So if I were to make this A, I'd do ABC and ABF. But if I make this B, I'm only gonna look at BC and BF.
I'm
And
not
then like
okay. I'm not sure we're walking down the same path right now. What do you want this dictionary to be used for?
I kind of wanted to be used to like prune down the remaining letters I could be looking at.
Okay, that's one way to think about it. What if I told you to think about it as what if we use this dictionary to see if we're on the right track?
Use this dictionary to see if we're on the right track.
Yeah.
Then do I only want the suffixes as my values?
Okay.
But like,
Sure. Sure. We can drop this for now. Uh, so the solution I was trying to push you towards was what if we kept a dictionary of prefixes? So A, AB, ABC, A, it's already in there. AB, it's already in there. ABF, G, GH, GHI. What could we do with this?
oh, we can see if the next substring is in the dictionary.
Right. And how would that be of use to us?
We can quickly check to see if the remaining letters are in the dictionary.
We can
Um,
quickly tell if we're on track, can't we?
yeah.
Yep. One final note.
Well, okay. So I guess like what said dictionary, so I assume that we would need to use a value for like somewhere. But if we use the set,
Yeah.
then I probably would have understood that better. Yeah.
Okay, maybe. The last thing I'm going to ask you is have you heard of what a trie is?
Yeah, I mean, yeah.
All right. This is a one of the classical trie problems. For the very beginning, I told you that we have unlimited memory, so we don't really care about that. We can construct this set. But if our dictionary is huge and contains every possible permutation of letters, that might not be very feasible, right? To keep track of this
Yeah.
set. Okay, cool. Yeah, I think this worked. Your implementation seemed okay. I had to give you a couple of major hints to push you along the right direction, particularly with how to think about your visited set as well as how we might want to traverse. But the actual implementation was a little bit solid. The biggest thing that I was concerned about is when we were performing the runtime analysis of this problem, you feel very pressured to give me an answer quickly. When I think that realistically, if you had thought about it for a minute, talked through components of what you were thinking, you might have been able to get the correct runtime without me kind of telling you what it was. So we've discussed this before. I'd urge you kind of not to guess. And if you really don't know, that's when you ask questions, right? You ask, um, so I'm having trouble determining the runtime of this particular component. Can you give me a hint? What is the this is what I know, this is what I thought of already. What do you think about this? Don't just kind of blurt out this answer that is a guess.
Yeah. Yeah, the runtimes of Raspberry searches are always like tough for me. Actually, yeah, now that I think about it, it's really just how many other paths I'm looking at to the power of um the maximum
Yep.
iterations I'm gonna go through. Okay, yeah, that's huh. I only just realized that.
All right, cool.
Uh
Well, that's all I have for you. We're at a This question was about 50 minutes, but I think when I started the follow-up, it was at like 35 minutes. So this question was done in, reasonable time. We're about at the almost 1.5 hour mark in total. How do you feel?
Um, I mean, yeah, I haven't seen either question before, but I have seen like very similar problems. Oh, actually, no. This one is the word search question, right?
It is the word search
Uh,
question. Yeah.
yeah, I did that like a long time ago. But yeah, I mean, like I guess me pivoting to implementing this recursively, um,
It was
that
good.
was like new to me. Never, I always just, you know, did a explicit stack iteratively.
Yeah,
And then,
you pivoted really quickly, actually. That was good.
um, okay, cool.
All right. Well, I'm
Yeah,
going to end the recording here. We can talk about some more stuff afterwards. I hope that you do watch parts of the recording to get a sense of timing. I think you probably know better than I do how you might explain some things a little bit quicker. The time is still somewhat of a concern, um, but I think that if you're able to kind of trim out some of the uh, minor, very obvious details, you could probably save 5 minutes. Mm, yeah,
oh, we never did like walkthroughs of like an example for this problem though, right?
that's
Like,
right. Because I saw the time, and I was like, okay, probably a little bit not. But instead, I gave you some follow ups, talk about hypotheticals. If you would like to walk me through this, we can, but I think it would be reasonably self explanatory. I think I had plenty of time to gauge how you were thinking about this as I kind of asked you about what problems you might run into.
yeah, okay, yeah, that's fair.
All right.
Um,
Then I will end this here. We can talk some more after. Sound good?
okay,
All right.
yeah.